Well, now is the time to start and apply Ampere's law in different cases, which are interesting and of daily importance for us. First of all, let's consider cylinder. If there is current flowing through cylinder, you see, when I'm talking cylinder, first we'll talk about cylinder, but ultimately we have to apply it to a current carrying thin wire. So when we are talking about cylinder, simply we are aiming at a thin wire. Current carrying cylinder is here. Suppose its length is L and radius is capital R. We have considered the point, you see, on the surface, inside the surface, outside the surface. So first of all, we'll consider the point P1 and you apply this theorem BdL, that is μ₀ into I. This dl, the circle that we are going to choose as Ampere in loop, will be a circle of a radius x. This distance we are going to consider x. So its circumference is going to be 2 pi x. This is μ₀ I. B you find μ₀ upon 2 pi I upon x. This is hyperbolic relation B proportional to 1 by x. This type of relation between the magnetic field and the distance. Similarly, if you consider the point on the surface itself that I have shown by the letter capital P, for this the distance is going to be radius of the cylinder itself, and this would be replaced by capital R. Then on the surface it's going to be μ₀ I upon 2 pi r, that's written over here. But when you consider the point inside the surface, you see, for outside point, you don't bother, you need not bother whether the cylinder given is hollow or solid. Both the cylinders are going to behave in the similar manner for outside points. But when it comes to inside, you will have to be particular whether it is solid or it is hollow. If it is a hollow cylinder, you see, inside the hollow cylinder, no current is enclosed. And when you will put here I equal to 0, obviously this is going to be 0. That means the magnetic field will be 0 inside the hollow cylinder. And this graph has been plotted. Inside the hollow cylinder, this field is 0, shown over here. All of a sudden on the surface, you find a peak value and then again it starts decreasing. Now, when it comes to solid cylinder, you know, in a cross section, the current will flow throughout. It is the nature of DC, direct current. When it flows through a conductor, complete cross section is utilized. Whereas, you know, this is a point to be highlighted because AC doesn't follow this rule. When alternating current flows through a wire, it is confined to the surface only. That's known as skin effect. So here, since we are talking about DC, DC will distribute itself throughout the cross section in such a manner that the current density always remains same throughout. For the whole wire, let the current density is J, and for a little thin wire, suppose this is of radius is smaller, it's going to be J dash. But we know that current density is same for throughout the cross section, and that way you find I upon pi r square. This is equal to I dash upon pi small r square. Pi gets cancelled, you get the value of I dash I r square upon r square. This is the current carried by thin cylinder within that thick cylinder of radius r. It's written over here, this value of current passing through thin cylinder. Now, on the surface of this thin cylinder, if you try to find out the magnetic field, you'll have to use the relation again, that of surface μ₀ upon 2 pi I dash upon r. This is the relation you are going to follow, and you'll have to put the value of this current I dash. Ultimately, you are going to get the relation for the magnetic field on the surface, that is B μ₀ upon 2 pi I r upon r square. This is going to be simply I. This is the magnetic field inside the solid cylinder at a distance small r from the axis. Obviously, this relation is linear, b and x, or you might say this distance is small r. So I'll better write small r only, and b is linearly related with this kind of relation you are going to have. And this graph has been plotted over here. Now, this we have considered. On the axis of both the type of cylinder, the magnetic field is always going to be 0. Similarly, the same very pattern is applicable for a condenser getting charged. You see, when the condenser is fully charged or fully discharged, it's not having any kind of current through it. But when the condenser is in the process of getting charged or discharged, there is displacement current through it. In that case, this is going to produce magnetic field inside it also, outside it also. That means a condenser having variable current always produces magnetic field inside and outside. The values are given for different points. You see, if the point considered is outside, like I have shown by the letter P1, point is outside, the field is going to be μ₀ upon 2 pi I, as it was here. For outside, I upon 2 pi. If you have chosen the distance x, it's going to be x. On the surface itself, near this surface, you'll find this to be r, μ₀ upon 2 pi. This is going to be I upon r. And if you consider the point inside at a distance is small r from the center, then in that case it is going to be I is small r upon r square. This is very important, and you must remember for the study of electromagnetic wave, you have prepared yourself at this very juncture itself. This will be required there. You must be aware of this thing, that a condenser that is in the process of charging, discharging, always produces a magnetic field within it and outside it.